Hi, today we're going to look for the seventh chapter, which is the air conditioning process. So this is the first part of the chapter 7. Mm, for air conditioning process, the definition for the air conditioning process is the process of treating air to control simultaneously its temperature, humidity, cleanliness, and distribution. So the definition of the air conditioning processes is not just with the reducing or increasing the temperature, but it also involving with the humidity, cleanliness, and as well the air distributions or the air ventilations. So the purpose of the air conditioning process um, to maintain the living space or an industrial facility at the desired temperature. So the living spaces, like for example the domestic, and then the facilities, for example the shopping mall, shopping complex, offices, then operation theater, which are required to maintain the desired temperature and the humidity. So each human, um, they have their own human comfort level zone, which is depend on the temperature and the humidity that can be accepted by the human. So it will depends whether it is going to be a heating process for the from the cold temperature to increase the temperature, which is the involving with the heating process, and then the cooling process, which is involving with the reducing the temperature. For example, from 40 degrees Celsius, we are in Malaysia living with the high humidity and high temperature, so we're going to increase the amount of the humidity. So that we need cooling process, and then also involving with the humidifying, um, which is putting some air, putting some of the moisture or water vapor into the environment, and then as well dehumidifying process. This is, for example, in the Malaysian environment, our humidity is very high, so that's required to reduce some content of the water content in the environment, so that will bring to the human comfort zone. So the application for the, for example, of air conditioning in the office building, residential, hospital, and as well for the clean room. So this is the engineering complex in the UiTM. So mechanical engineering in this section. At the moment, the wet cooling, the air conditioning process for the UiTM, this engineering complex is not working due to the several factors, which is a good point for us to do the study. Okay, so air conditioning is meant to provide a comfort zone, not a cooling zone or not a heating zone, which human's body can have a comfort levels, which depends on the three factors: temperature, humidity, and as well air motion. So human comfort zone, the temperature range between 22 degrees Celsius to 27 degrees Celsius is depend on the human itself. It depends on the different perspective of the people, and as well the humidity level between 40% to 60%. So humidity here means that the relative humidity. Okay. So the terminology for the humidity we're going to look in the next slides. Yeah? And then also involving with air motion, which require the air ventilation, and as well depends on the air velocity, and such other factors which is also affecting the human comfort zone, such as the air cleanness and odor, and as well on the radiation, which is involving with the heating. Okay, before we proceed to the air processes, we have to understand the condition for atmospheric air. So the atmospheric air, it is contained of the air mix, it is the air mixture which is contained of the nitrogen or the gases. Okay, so this is we call as the dry air. Okay, or the gases, this is known as the dry air. And then it also contain of some of the vapor. Okay, so thus the atmospheric air is the combination of the dry air, which is the dry gas from the gases, which is the gases contain of the nitrogen, oxygen, and small amount of the other gases, which is the oxygen 28%, and nitrogen 72%. Okay, and these dry gases plus with the water vapor or moisture. Okay, so the combination of the dry air plus with the water vapor, this is the what we call as the atmospheric air. So the atmospheric air where we have today, which is at the standard condition, we call it as the standard atmospheric, which is for the pressure we have the standard atmospheric pressure, and then for the temperature, standard atmospheric temperature. So the standard atmospheric pressure, which is equal to 101.325 kilopascal, and then standard atmospheric temperature, which is T 25 degrees Celsius or 298 Kelvin. So these two, if we look again, the temperature in the air conditioning process that we are going to be interested to analyze, which is in between -10 to 50 degrees Celsius. Okay, so with these conditions, we can treat that the dry air, the specific heat constant for the dry air, the value is at the almost at the constant level, which is equal to 1.005. So with the assumption that the operating condition for the dry atmospheric air, we can say that the specific heat constant for the dry air can be assumed to be at 1.005 kilojoule kilogram Kelvin. So taking 0 as the reference temperature, the enthalpy and the enthalpy change of the dry air can be determined as the enthalpy equal to Cp times with the temperature. So thus the temperature change, the enthalpy change delta H for that range is equal to Cp times with the delta T. So at the 50 degrees Celsius, the saturation temperature, the saturation pressure for the vapor is at 12.3 kilopascal. And at the pressure below at this value, the water vapor can be treated as an ideal gas. So even it is a saturated vapor. So thus, with these conditions, the saturated pressure, if you look into the temperature entropy diagram, and this is the temperature entropy curve. So this is the constant pressure conditions. Okay, so this is the where this is a saturated T saturated. So if you want to look for the saturated pressure, we have to look on the pressure enthalpy, which is something like this. Okay, so this is what we have for the P saturated. So this is where the condition of the saturated or superheated vapor. Okay, so this is where the condition for the saturated vapor, P saturated. Okay, so the atmospheric air can be treated as an ideal gas mixture, which is whose previously we have the atmospheric pressure, which is contained of the dry air and water vapor or moisture. So thus the presentation of this as according to the Dalton's law, the partial pressure for the dry air and for the water vapor is the summation of the partial pressure plus with the summation of the partial pressure for the water vapor will be equal to the pressure for the atmospheric air. So the atmospheric air can be treated as an ideal gas mixture whose pressure is the sum of the partial pressure of the dry air and the water vapor. So this is the atmospheric air and this is the dry air and this is the water vapor. Okay, so the water vapor pressure will be differ as according to the conditions. So for example, when the conditions of the saturated or the this is the temperature constant line moving. So with this operating conditions, the pressure for the our pressure point for this constant temperature will be different. So I will redraw this. For example, for the pressure enthalpy diagram that you have here. Okay, for example, where you have here the conditions of the temperature and the pressure. Let's say that this is going to be the saturated pressure. Okay, so either it is going to move there or here for the saturated pressure. So when in the normal conditions the saturated the water vapor exists at the superheated regions. So when it is moved, it will become as the toward approaching to the saturated condition where the water vapor will be changed into the saturated liquid conditions. So the enthalpy for the water vapor in the dry air, in the atmospheric air can be taken to be equal to the enthalpy of the saturated vapor. So thus at the same temperature, so which means that the enthalpy which is equal to enthalpy at the G condition. So which is, if we take this one, enthalpy plus this is the pressure enthalpy. So the enthalpy will be in these conditions, okay, at this temperature point. So the enthalpy of the water vapor can be determined approximately. So if we look on the properties table for the water. So if you look on that property table for 0 degrees until 50 degrees, okay. So for the 0 degrees, so the value for the Hg is equal to 2500.1 to 2501.3, and then it is a slope. So if you plot a graph, which is what you get is something, this is the enthalpy and this is the temperature, so something like that. So the graph slope for here, which is the m value, is equal to 1.82. So if we take y equal to mx plus c, so where c is equal to 250.13, to 50.3, our slope is equal to 1.82. So this is how the formulation coming out. Okay. Okay, let's look some terminologies that we have. So the first terminology, important terminologies, which is the specific and relative humidity. So what is the specific humidity? Specific humidity is the measure of the water vapor in the air. So it measures the ratio between the amount of the water vapor to the amount of the dry air. Where the specific humidity, from this equation, what we have is that if we take the ideal gas equation of state, PV equal to mRT. Okay. So from what we have here, the mass is equal to PV over RT. Thus, the omega, or the relative specific humidity, which is the mass flow, the mass between water vapor. So this is the water vapor, and this is the mass for the dry air. So if we take this equation, PV over RT for the dry air, sorry, for the water vapor, over PV over RT for the dry air. So let's assume the temperature is similar, is constant. The volume is also constant. Okay, because this is contained, let's say that this is contained in a box. Okay, so the volume is similar. Okay, it is mixed in similar temperature and in similar contained. So V and temperature can be cancelled out. So thus the remaining is P. What is that? Is a PV over PA, and then R is gas constant, RA over RV. So RA is a gas constant for the dry air, and RV is a gas constant for the water vapor. So gas constant for the dry air, RA is equal to 0.287 kilojoule kilogram Kelvin, and RV, gas constant for the water vapor, is equal to I think this is equal to 0.4 something, 0.8 something like that. Yeah, 0.8314, something like that. Okay, so if you divide 0.287 divided by 0.8314, so it will give you 0.287 divided by 0.8314. Oh no, it's not 0. Something, should be okay, but yeah, 0.34, 0.287 divided by 0.83. No, I think this is about 0.45 or something like that. 0.45, something like that. 0.45. But anyway, you can check the water vapor gas constant, which is the ratio between that, give you about 0.622. Okay, yeah, this is equal to, the RV is equal to 0.4614 kilojoule kilogram Kelvin. Okay, So another important is the relative humidity. Okay, so the human comfort zone level depends more on the amount of the moisture content. So the previous one is the amount of the moisture that contained in that atmospheric, but the value will be varies. The value will depends on the temperature conditions, and too much value of the water vapor will give uncomfort conditions to the humans, because you're going to get easily to be sweated in that environment. So thus the amount of the water contained should be look as well on the how much the maximum capacity of the water moisture that can be contained in that environment. So in this case, the scientist has come out with a new definition, which is called as the relative humidity. So the relative humidity will give you the information about how much the water vapor or moisture content that can be held by the atmospheric air in that conditions, so that the level of the human comfort zone can be monitored. Okay, so the ratio of the ratio of the humidity or the relative humidity is provided by the amount of the moisture that can be held, okay, relative to the maximum amount of the moisture that the air can hold at the same temperature. So again, if we use the ideal gas equation of state, where PV equal to mRT, where the symbol for V referring to the water vapor and G for the saturated conditions, where the temperature or where the moisture content achieved at the saturated conditions, the probability of the maximum content that can be held for that temperature will be limited. So thus some part of the moisture will be dropped as the saturated liquid. So with that conditions, mv divided by mg, so thus what we have here is PV over RT, which is for saturated vapor or the moisture, and then PV over RT, saturated vapor conditions. So volume similar, temperature similar, R is also similar. So thus what we have is only depends on the ratio PV over PG, where PG will be depends on the temperature conditions. So you can look at the table how much the amount of the PG that condition contain. So if you have the temperature and you have the relative humidity, then you can find the value for PV. Alright, yeah, so this is the equation where PG is equal to P saturated at that temperature. So if we both combine the equation for the relative humidity and the specific humidity, so this is what we get, the equation. So you don't have to remember this equation just to understand how that it can be derived. So another important criteria is to look on the enthalpy. So enthalpy of atmospheric air is expressed in the per unit mass of the dry air. instead of the per unit of the air-water vapor mixture. So the enthalpy of the atmospheric air is the sum of the enthalpy of the dry air and the water vapor. So this is enthalpy for the dry air, and this is the enthalpy of the water vapor. So the enthalpy for the water vapor, if you recall in the previous, which is HV equal to Hg at temperature. Okay. So from this, which is MAHA enthalpy for the A and MVHV, if we look dividing into the mass of the dry air, so what's remaining is that enthalpy of the dry air plus with the MV over MA, which is this is the specific humidity. So the enthalpy of the atmospheric air is equal to HA, okay, HA, which is previously we used the Cp is equal to 1, H is Cp times T, Cpa times with the temperature at T, temperature. So, and plus omega Hg, where omega is the specific humidity. H is the C, which is specific heat at a constant pressure, 1.005 kilogram degree Celsius. So ordinary temperature for the atmospheric air is frequently, so this is this temperature usually we call as the dry bulb temperature. So we're going to look another one which is called as wet bulb temperature. So this is an example that you can use this, you can do this example by your own. You have the volume, okay, just use PV equal to MRT, 25 degrees Celsius, so this is a 298. The pressure that you have, P equal to 100 kPa, temperature 25 degrees Celsius equal to 298 Kelvin. Volume you have 1525 times 3, 75 m3, and then relative humidity 75%. Okay, so yeah, you can what is a partial pressure for the dry air? Determine PA, which is equal to P minus PV. So PV, you can get it from here. The specific humidity, so this is the omega equal to MA over MV, or 0.622 PV over PA, and then enthalpy, and then so on. So you can do it on your own. What does it mean by dew point temperature? So another important parameters or important variables that you have to understand is the dew point temperature, which is the dew point temperature is defined by temperature at which the condensation will start to happen. So if you look on the temperature entropy diagram, Ts, so this is where the temperature will start to begin. The condensations will be happening. So when we involve it here, so when the temperature go into this condition, it will start to condense, because it is already in the saturated liquid plus with the saturated vapor regions. So the dew point temperature is when the temperature is equal to T saturated. Okay. All right. So I'm going to look detail on that. And then for the adiabatic saturation, which is another way to determine absolute. Okay, so this is how to determine the relative humidity. Yeah, so when the pressure, so this is the temperature entropy diagram. When it is in these conditions, okay, dropping and then go into the saturated condition. Okay, so when you have that, this is the energy balance and this is for the, for the water. you can do this, you can refer this into the lecture. Okay, and then finally the wet bulb and dry bulb temperature. So wet bulb temperature referring to where the temperature of the water vapor. So wet bulb is read from the wet bulb thermometer. So in order to read, this is a sling psychrometer to read the wet bulb. So how to read this one? There is a handle here and this is a bearing. So what does it mean for? So to measure the wet bulb temperature using the wet bulb thermometer, you need to rotate, or you need to rotate this sling psychrometer in order to produce an airflow. So with this, it will read the wet bulb temperature of the weak moisture. So it cannot be read in a static condition. So you have to rotate this, and then for the few minutes, and then after that stop the sling psychrometer, and then immediately read the wet bulb thermometer and dry bulb thermometer. And this is another important devices to read the wet bulb temperature. So why do you need this wet bulb and dry bulb value? Because you need this to refer into the psychrometric chart. So in the next slide, we're going to look on the psychrometric chart. Yeah. And then in order to read the wet bulb temperature, you must have a flow for the air. Okay, so the airflow coming in, so the weak thermometer will be put in there. Okay, so this is an example. Okay, so this is a psychrometric chart. The psychrometric chart is only applicable for to do the analysis for the air conditioning processes. So it's only applicable for the temperature, for the pressure is at the atmospheric conditions, which is equal to 101.325. Okay, so what do you have here in the psychrometric chart? So firstly, previous you have the measurement for the temperature, which dry bulb temperature and the wet bulb temperature. So you will refer these two values or two variables into the psychrometric chart. So here you have the dry bulb temperature by reading from the thermometer. Okay, and then you have another one here which is called as the wet bulb temperature. Okay, wet bulb temperature. So let's say that you got the reading dry bulb temperature equal to 30 degrees Celsius and the wet bulb temperature equal to 25 degrees Celsius. So if you plot this and come here, then you can read the point will be in these conditions. Okay, so what else? The parameter or variables that you have here. So firstly, you're going to look here the value for 40 degrees and 30 degrees. So what is the 40 and 30 degrees? This is the relative humidity. Okay, so this is the relative humidity line. Okay, and then this relative humidity line is when you go lower, the amount or the value for the relative humidity will be dropped, which means that the higher the wet bulb value, the dry bulb value, the lower will be the relative humidity, or the higher, the lower the value of the wet bulb temperature, the higher will be the higher of the wet bulb temperature will increase the relative humidity. Okay, so if you go here 30 degrees Celsius, then you increase the wet bulb temperature is increased. Okay, if you look here 10, 15, 20, 25, if you are constantly increase at this region conditions for 30 degrees Celsius dry bulb, then you will meet with 30 degrees Celsius for the wet bulb. So the saturated when T wet bulb equal to T dry bulb, it is when the relative humidity will be equal to 100%. Okay, so when the wet bulb is increased until it achieves the dry bulb temperature, so the relative humidity will be increased until it is achieved at the relative humidity equal to 100%. So what will happen after that? So there will be no more energy stays constant at the 100% relative humidity. So on the right, on the y-axis is the specific humidity. Okay, so this is a specific humidity. So like here, 2, 4, 6, 8. So this is the specific humidity. Okay, and then in these sections, if you have here meeting that point, this is the enthalpy. So this is the enthalpy line H. Okay, and then you have as well, this is the volume cubic meter or the specific volume. Okay, so this is the dry bulb, this is the wet bulb, this is the enthalpy, this is the specific humidity, and this is the relative humidity. Okay, so in order to simplify of the psychrometric chart, it will looks like this. Okay, dry bulb, specific humidity. This is the saturation line. Then it will decrease the saturation line across that specific volume, and then the specific enthalpy. So you need to understand this psychrometric chart. It only can be used at 101.325 kilopascal or at the standard atmospheric pressure. So this is another example. You can do this at the